Hi everyone, I'm Roderick Reber from Arkema, North America. I'm going to be talking today about designing polymeric materials for additive manufacturing. I'm going to go through these slides, kind of hopefully you have some questions at the end. I'm in applications development here at Arkema Inc. in King of Prussia, so just outside of Philadelphia, but we're a global company. Just an overview of what we'll talk about today. We'll go through my background experience, give you a little perspective of where I'm coming from in my perspective on design of materials. We'll keep this from being too much or at all a commercial for Arkema's materials, but just to give you a perspective of where I'm coming from. We'll talk about designing materials for FFF or extrusion printing, which is my personal area of expertise. We'll go through a case study of designing some capstan PEKK materials. And then we'll go through designing powder materials for selective laser melting processes. So we have an example from our polyamides group, but we'll discuss how this relates to all materials, all polymeric materials, and how it could be applied to basically any material for SLS or other laser sintering, laser powder consolidation processes. So just very, very quickly, Arkema is a provider of high-performance materials. This is our lineup of high-performance materials in our newly formed business unit, High-Performance Polymers. We offer Kynar PVDF, fluoropolymer, well known for its chemical resistance, UV resistance, real sand polyamides, a wide range, including bio-based options. Capstan PEKK, the division I currently work in, it's an ultra high performance polyaryl ether ketone, and PVAX elastomers. So Arkema has been supplying materials into additive manufacturing since the very beginning of the processes, kind of with our Sardimer business unit, the original UV curing process, and providing powders into the laser sintering process since the very beginning. Our lineup of high-performance polymers for both SLS and FFF includes some grades that happen to work well as some grades that we've worked with manufacturers to purpose design for additive manufacturing. Personally, I've been with Arkema for 10 years, 6 years working in Kynar PVDF, and the past 4 working in Capstan PEKK on specifically additive manufacturing applications as well as general purpose technical service here. I'm the global technical lead for Capstan FFF. Under design of materials for FFF, not all polymeric materials are suitable for this process. If we look at the subset of materials that are available versus the subset of entire thermoplastics, it's a much smaller subset. For the most part, these materials are amorphous polymers. It's important to also note that an injection molding data sheet does not necessarily mean a printed part data sheet. So the properties that we're getting with injection molding don't necessarily match the properties that we'll get with a printed part. Also, it's important to note that a filament data sheet doesn't necessarily mean your part data sheet. So as this process evolves, it's very kind of processing conditions dependent, and that your printer may not be able to achieve the ideal properties, ideal conditions to make this material, and therefore you might not be able to get idealized data sheet type properties. You may be able to do better, but it depends on exactly the processing conditions. So it's important to note what the processing conditions were in a data sheet. As well as there's some special considerations for material design. So we can't necessarily incorporate all the additives or all the grades that we otherwise would have. The particular FFF challenge is it's mostly limited to amorphous polymers. Crystallization competes with layer adhesion. So therefore, we're limited, as I mentioned earlier, to mostly amorphous polymers. However, there are some workarounds to be able to get to semi-crystalline polymer, which offers better chemical resistance, high temperature properties, and mechanical properties such as creep, etc. And as a general rule of thumb, printing difficulty increases with glass transition temperature. So a higher TG polymer is more difficult to print. If we look at the spectrum of difficulty to print, goes from kind of PLA, TG below 100 degrees to, polyether imide or PPSU, TG, which is well above 200 degrees C. If we look at the FFF process, we kind of can can separate it into inputs and effects in the entire process. So we're starting with a polymer. The polymer needs to be compounded with its additives, or at least made into pellets. Those pellets need to be made into a filament, and then those filaments need to be printed. So each one of these steps kind of has its own set of requirements that affect our material design. When we're at the polymer, okay, we're talking about chemistry. Which polymer do we start with to begin with? What's the molecular weight of that polymer? Molecular weight impacts viscosity. Okay, kind of I use them one and the same. When we're going into compounding, it's what additives do we select? What additives, what level do we add those additives, and how do we disperse those additives? Now, these things might affect filament extrusion. Is the viscosity suitable to make a consistent filament? Does the polymer have enough melt strength to extrude through an extruder, make into a filament that is a consistent diameter, spool up at an acceptable feed rate? Can we spool the filament? Okay, does the additive make the material too stretchy, too brittle, etc.? And kind of all in all, how consistent is this process? And then from there, we have to go and print the material. So can we handle the filament? Is the filament stable enough, strong enough, not brittle, not too brittle to be printed? Does it flow in the nozzle appropriately? So this is kind of a unique process in that there's very low shear and kind of very, very short residence time in the hot zone of a nozzle. And this is an advantage in some ways, but it also kind of leads itself to its own challenges. Do the layers stick? So is there too much crystallization? Is there too much thermal contraction that might cause warping? Will the additive package that we added into the polymer cause excessive nozzle wear? And then finally, what are the mechanical properties of the printed part? So just very quickly, we'll go through one example of a carbon fiber filled PET grade. So our standard injection molding carbon fiber filled PET grade is called Capstan 8010 C30. And as is convention when designing a injection molding carbon fiber filled grade, we basically want to load up as much carbon fiber as is practical and maintain the fibers to be as long as possible to maximize the mechanical properties. So we're basically we're compounding an additive package that basically maintains the carbon fibers as long as possible. We're not so concerned with molecular weight and viscosity because it's being processed by extrusion or injection molding that can handle these higher molecular weights. And since we want to achieve the maximum crystallinity, highest thermal properties, we're using the fastest crystallization, highest melting point grade for PEC. Now, if we tried to just make FFF parts out of this, it's possible, but it's really allows itself for a lot of challenges here. So we end up with a brittle filament that has kind of, I call it fur, but it's really just carbon fibers, and leads to clogging of the nozzle in the printer. We get poor flow in the nozzle. The filament is also, I forgot to mention, is also terribly brittle in that if we go to spool it around a spool, it tends to just crack because it's, we're basically trading off stiffness versus toughness. And in the end, we get poor layer adhesion because we've got too much carbon fiber in there. The carbon fibers are too long and too oriented in the flow direction. And the material is crystallizing too quickly in order to get layers to adhere. So if we think of, okay, we're going to design an FFF compound for such thing, we have to reconsider, okay, we'll add milled carbon fibers at lower loading. So we'll get a balance of stiffness, toughness, and good filament surface finish. We use a lower molecular weight, so we'll get good flow in the nozzle. And we use a lower melting point or slower crystallization grade to get strong layer adhesion in our material. Just one example, and kind of this thought process goes through any design consideration when making a filament material. There's an important step to consider in that your material has to have good mechanical properties, but also has to be able to be made into a filament and also then printed. Just an important thing to note is even if we start with just a basic material, this is just Capstan PEC A. So this is the slowest crystallizing pseudoamorphous version of PEC. Your mechanical properties depend on your print conditions. So PEC A is an extremely easy to print high temperature polymer However, your properties really vary depending on what printer conditions you can, from nearly isotropic, best in class properties to still pretty good, but okay, you have to consider that your properties might not be so isotropic, and that your layer adhesion will definitely be weaker than your extrusion direction properties. Okay, on to design of materials for powder bed fusion processes. This is again related to mostly to polyamides, but if we consider the example here and we go forward, it applies to all materials. So the same guiding principles apply to design of Capstan PEC powders. So Capstan PEC is one of the unique materials in that it's available for both FFF and laser sintering because of its tunable crystallization. An example with polyamides that really kind of gets into the point that it's a much more complex process as we move into polyamides. So here's a chart that one of my colleagues over in France gave me, is all of the related properties and how they relate in a FFF, in a SLS process. So it's very complicated. We won't go too into detail of this, but you can see that when we're talking about a powder material, we have not only the base material properties, the additive properties, but now we have the powder flow properties, the size, the morphology, the particle size distribution, all of this that really influences it. So we'll try to focus on a few of the key things that are really focusing here. But basically, the key point is it's much more material dependent, much more specific, because we have just so many complex interactions that it's much easier for, say, some intermediate to design their own FFF material with the guiding principles that we discussed than it might be necessarily for an SLS material, because we have to go all the way back to the fundamental powder as kind of the raw starting material. So important thing to note is particle size distribution is one of the key things that we highlighted. The key aspect is not having a large particle size tail. This really influences the bed dimension, the rakeability as a new layer of coat, and the packing density. So if we're not dealing with a lot of large particles in there, this really influences the packing density. And we think of a laser melting process, and we're depositing a layer of powder. That has to be pretty close to the final part density as we melt it. The further away it is from the final part density, the more shrinkage, warpage, porosity, et cetera, that can come with this process. So kind of the key thing is reducing the upper particle size. This is our key guiding principle here, which can be difficult depending on the method of which the powder was made. Was it ground? Was it synthesized in a spherical way, et cetera? Sorry. The next is thermal properties. So thermal properties is the material needs to have a unique combination of a big sharp melting enthalpy, a narrow melting point, and a slow crystallization. So kind of if we look at this DSC scan, kind of material one has got kind of these weird recrystallization, melting peaks. There's kind of disorganization in the melting, whereas more idealized material two has very sharp melting point. So we can maintain this printing bed in this range here, where we're getting a little bit of bed adhesion, add some additional laser energy, have a very sharp melting point, and then go through the coalescence process. So this is kind of a fundamental materials design decision, is we need to pick from materials that can be or fundamentally have sharp melting points, or it can be heat treated to such that have very sharp melting points. The next is crystallization rate. So the material needs to also have a sharp melting point, but yet slow and controllable crystallization. So the material in this powder bed is maintained at this elevated temperature and has to crystallize slowly to reduce curling and warpage and improve the coalescence. So as we deposit a layer, it needs to crystallize, but not too quickly that the previous layer is not crystallized as the next layer is deposited. So in order to get, again, layer adhesion, this is the fundamental crystallization competes with layer adhesion problem. Also, it reduces part warpage in general. The next is coalescence. Okay, coalescence, the particles have to coalesce well, and it has to be a suitable low viscosity because you think there's zero shear on this process, that we're just hitting it with a laser, so the two particles need to flow together. So as a lower viscosity is generally preferred because we can't really change the surface tension, and the particle radius is defined by what is most flowable. And the next, kind of most important in my view, is recyclability. So powder bed fusion process, at most, maybe a little bit more than 15% of the cake so the cake is this entire bed of powder, is made of into parts. The rest has been maintained at this high temperature without shear for a long time. And so we need to worry about coalescence of the powder as well as degradation or molecular weight control. So a lot of these polymers at elevated temperatures like this will want to coalesce, and kind of you can see kind of a polyamide example of something that was simulated over a long time, has been heated, and kind of we get this both darkening, coalescence of the powder. So we're getting kind of almost like cold sintering where the powders begin to bridge together, which affects the flowability, affects all those previous things we discussed. And an increase in molecular weight, which is then, decreasing the flowability as well as yellowing. So this is the same issue with polyamides powders as well as PEC powders. So we've put a lot of thought and effort into making the powders as recyclable as possible, because we have 85% of this powder that we need to recycle, or else the process just becomes unsustainable. Okay, if we use, this highly designed powder and we're only end up using 15% of it, the part process really goes way up. So if we design the powder so it can be recycled, design the process so the powder can be recycled, we can really end up recycling most, if not all, of this powder for at least a few runs. So in conclusion, we have to consider that these unique processing methods in additive manufacturing are the guiding principles for designing of materials in additive manufacturing. Now, when we go through and we consider how materials were previously designed for polymeric processing, it's a bit different than having to go through this intermediate step of making a filament or making a powder and dealing with these low shear, low pressure additive processes that we're dealing with now. In general, slow crystallization is needed for SLS. It's a plus for FFF, and a lot of materials in FFF are more amorphous than semicrystalline, or actually are from the amorphous polymer family. In general, molecular weight and viscosity are a key factor for both processes. Generally speaking, we're on the low end of molecular weight in terms of what's suitable for melt processing, because we're in this low shear, low pressure domain. So we need good low shear, low pressure flow to get good adhesion. However, we need to consider that we also have to maintain a high enough molecular weight to maintain the mechanical properties of our polymer, of our part. Additives and fillers must survive the powder or filament process. So when we consider a fiber additive, a platelet-like additive, et cetera, we have to consider that how it will influence either the filament or the powder flowability, the powder recyclability, the powder particle size distribution, et cetera. With filament, a non-machine specific solution may be possible. There's a lot of materials out there that are kind of for the open printer, open materials world that more or less can be printed on any printer, provided it meets the requirements. Your performance may vary depending on the printer that you're selecting. However, with powder, there's so many parameters and so many aspects of the powder that things may make the design much more specific. So it's something to really keep in mind, that making a powder is orders of magnitude more difficult, more complicated than, say, making a filament material for additive manufacturing. And with that, I'll turn it over for questions.